7.4 Characteristics of logarithmic functions with base 10 and base e. Now, a logarithmic function is a function of the form y equals a log base b x, where x must be greater than 0, b is also greater than 0, a cannot equal 0, and b cannot equal 1. Now, the cool thing about it is that a and b can be any rational number. So another thing to remember, if you see a log without a base, without that b part, you can assume base 10. So for example, if you see a function y equals 7 log x, sorry, I was going to make that look too basey, x, that's just the same as y equals 7 log base 10 x. Now this feels a little bit weird, because we're not giving any kind of rules to it. At least with exponents, we knew like an exponential function is y equals a times b to the x. Okay, we kind of understand that, oh yeah, okay, it's a function with the variable in the exponent. Well, exponents and logarithms are related. They are simply inverses of each other, and I'll show you that in a second. If I were to say log base 2 32, the answer here would be 5. Basically, a logarithm asks 2 to the what is 32? That what is 5. Let's try it again. Log base 3 9. So 3 to the what is 9? Oh, I know. 2. Another example could be, and I'm just going to throw out a weird one, log base 5 of 1 over 25 equals, it's asking 5 to the what is 25? Now think back to grade 10 intro applied pre-cal. 5 to the negative 2, because 5 to the negative 2 is just 1 over 5 squared, which is 1 over 25. These nitty-gritty details are not important necessarily in knowing how to graph these things, because we will always be able to use the graphing calculator, but I always find it a little bit easier if I know what the heck I'm doing and where these numbers are coming from. It tends to stick more than if I'm just memorizing logs or whatever. So in this unit, we're going to mainly be working with logarithms with a base of 10 and with a base of e. Remember Euler's constant, e to the x, and we graph that? Well, there's a really important logarithm with the base of e, and that's our ln x. So logarithms with a base of e are expressed as ln x. And let's just go through some tables of values for specific logarithmic functions of base 10. So we're going to graph this thing. I've already given you the values here. Now what I can actually do is I can go here, I'm going to hit on, thank you, and I can go here and I can say, okay, I can put this into my y equals. I'm going to say log x. Now, on some of your calculators, you're going to have the options of putting different bases in. You can either put base 10 or you can just leave it as log because that's the same thing, and we're going to graph it. And I'm going to zoom in. So we're noticing this asymptotic behavior that's happening right here. Now, it looks like it's going right into it, but if we were to zoom in right there, it would get super, super, super close, but it would never actually touch 0. We're noticing here that at 0, it's actually undefined. However, let's get our scale in here. Let's start graphing this thing. So this is x, and this is y. And this is an arrowhead. So if I were to say x equals, and let's give ourselves a scale here, 1 and 1. That's all you need to do, by the way. I don't have to go 1, 2, 3, 4. I can just make sure that I have my scale knowing that one block this way is 1 and one block this way is 1. So at -1, at x equals -1, it's undefined. No value there. At x equals 0 right here, it's also undefined. Well, no value there. At x equals 1, it's 0. So this right here is our x-intercept. At 2, it's 0.3. So it's 0.3, about there. And then, it's going to be, why do you do that, silly guy? And then it's almost going to be half, at 2. And then it's a little bit more than half, 0.6. And then at 1, 2, 3, 4, 5, we have a little bit more until we get to 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, just one more. I'll just add it. So that when we get to 10, we are at 1. So if we're to connect these dots here, what I'm going to go is oh no, I don't like that. So we're just going to cross at 10, and it looks like that. What happens here is this right here will become an asymptote. So what I want to do is I want to just get super, 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 super close, but it will never touch. Now, I just want to remind us of y equals, of the graph of y equals 10 to the power of x. Now if we were to graph that thing, what would actually happen here is it would be reflected, in the line of x equals y. Or y equals x. We can do it that way too. That's a little bit more standard. So when x equals 1, y equals 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, we've got the same problem. And when x equals 0, y equals 1. And on an increasing exponential curve, we're getting super, super, super close to 0 here. So this guy right here is y equals 10 to the power of x. You're noticing here, equidistant, okay, from the line here. Essentially, this is like a mirror is being set up here, and this is the same distance from this point to this line as it is this point to this line. So it's just a mirrored image. So what's important to just realize that exponentials and logarithms are related. Okay, it's just logarithmic graphs are just the exponential graph, but mirrored in the line y equals x. Let's graph let's graph this next one. I'm going to put all my arrowheads on. Boot, boot, label it. Boot. Gonna make sure that I have my scale. 1, 1. So again, when we have g of x equals 2 log base, log 2 log base 10x, or just log x, we can put this into our calculator. Okay, and I'm going to go y equals, and I'm going to graph 2 log x. So remember, 2 log base 10x is the same thing as 2 log x. Let's graph it. See how it looks a little bit different. The second one that we just graphed is going to have the same intercept, but we'll jump up a little higher, a little faster. So at x equals 10, y is going to be 2. And just make another one here. So it's going to go like this. And so our x-intercept here is always going to be at 1, 0. We're going to look like that. And we're going to graph like that. So we're noticing that we're still having that asymptotic behavior here in the y-axis, or when x equals 0, but it jumps up a little further. Let's make a prediction here. What about this one? 5 log base 10x. This right here, we're still going to have the same x-intercept. The only thing that's going to change is how fast this thing rises. Let's graph it. So if I were to take my graphing calculator, and now instead I'm going to type in this formula. I'm going to go 5 log x, graph it. Whew! Look at that. It's actually jumping out of the scale a little bit. If I go window, I'm going to change my x max to 12. I'm going to change my y max to 7. So this right here is our 10. So at 10 we can see that it's 1. At 10 with the second one we can see that it's at 2. And at 10 you can see that this one is going to be at 5. So if I were to graph this thing, make sure I have my scale, 1 and 1. 1, 2, 3, 4, 5. I'm going to make an extra little tick mark because it's only 9. Good golly gee. So then this is going to 1, 2, 3, 4, 5. So this is how I would quickly draw it. Make sure that you have one point there, and it's going to be asymptotically getting closer and closer and closer to the y-axis. And if we wanted to graph it really precisely, we could use these points here. But using what we know of logarithms and what the leading coefficient means, we can graph it a little bit quicker.